Thank you. So this is joint work with Moshe Babaioff and Assaf Romm. And let's start. So school choice, as we have all heard, has become increasingly popular in many districts around the world. And by far the most common mechanism is actually not deferred acceptance that we've heard about in the past few talks, but what's called the Boston mechanism, also known as immediate acceptance. This mechanism is very simple and very intuitive to describe. And in fact, in some municipalities, it's carried out manually using spreadsheet software or even using a pen and a paper. So what's going on is that given rank order preferences, we greedily maximize, first of all, the number of students who get their first choice. So you can think about everyone applying to their first choice, and wherever there is enough room, everyone gets immediately accepted, and wherever there's over application, then as many people as possible get accepted. And whoever doesn't get accepted in the first stage, we then try to maximize the number of students who get their second choice, so they're applied to their second choice. We accept as much as possible, etc. And a major drawback of this mechanism is that it's susceptible to strategic manipulation. For example, if I don't have a shot at my top school, I should not rank my top school. I should rank my second option first so that I get there in the first round. That increases my chances of being admitted to that school. And this raises, of course, the question of, do students benefit from or are they harmed by using a manipulable mechanism? Seems like a straightforward question, but the answer is not straightforward. For example, there's a paper by Abdul Kadiroglu et al. From 2009 that showed that actually the fact that BM is manipulable means that in an equilibrium, it expresses also the cardinal utility level of the students, even though you only specify ordinal preferences as input to the mechanism. And more importantly than that, we're going to ask, do students from more sophisticated or more informed populations get an unfair advantage in using a manipulable mechanism than students from sincere or uninformed populations? So a very useful benchmark to compare BM2 is deferred acceptance that we heard a lot about. In particular, this mechanism is strategy proof, so it does not give any advantage to sophisticated students, to students who understand how to manipulate. And it actually also replaced the Boston mechanism in quite a few school choice systems, so the comparison is particularly apt. And we will say that a student has positive absolute gain if her expected utility under BM in equilibrium, we'll talk about equilibrium selection soon, is higher than under DA. And we're going to say that a student has positive relative gain with respect to a more sincere counterfactual version of herself. We'll define this if she has higher absolute gain than that counterfactual version. So if her gains in BM versus DA are higher than what her gains would have been in BM versus DA had she been more sincere. Note that since both the counterfactual version and the original version get the same outcome under DA, this is equivalent to comparing her utility under BM to her utility under BM had she been more sincere. And these questions of absolute and relative gain have been studied by Patak and Sonmez in a strict school priority environment. Note that strict means that the priorities of the school are strict. The priorities of the students we always assume are strict. And notably, we'll talk about this, the absence of ties is crucial for their analysis. Nonetheless, real school choice environments usually have highly coarse priorities to the extent that many schools have, say, 2 priority classes. Walking distance have a higher priority, and then there's all the rest. So we're going to ask today, do real school choice environments where there are a lot of coarseness in the priority, do they have qualitatively different behavior than that identified by Patak and Sonmez? So let's start talking about relative gain. Would one be better off belonging to a more sincere or to a more sophisticated population? So I'd like to remind you that both versions get the same utility under DA. So we actually compare welfare utility under BM. So if one's sophistication level is private, one can only gain by being sophisticated, right? If I'm sincere, I'm forced to rank the truth. If I'm sophisticated, I can also manipulate. So that's not a very interesting question of, in this case, when my sophistication level is private, will I be better off being sophisticated? But even if my sophistication level is private, my population's sophistication level may certainly be common knowledge. So the question here, would I rather belong to a more sophisticated reputation population and be more sophisticated, or belong to a more sincere reputation population and be more sincere? And so at this point, you're going to ask, well, you're mixing a lot of things together, because if you belong to a more sincere population, your competition is also from your own population. They're going to harm you less. So let's abstract away from all of that and assume that the size of each population is 1. So the reputation of my population affects only myself. And we're going to ask the question, under BM, would I be better off being sophisticated and having everyone know that, or being sincere and having everyone know that? And Patak and Sonmez say that in a strict priority environment, in the special case where priorities are completely strict, it's always better to be sophisticated, even if everyone knows that. And our question, once again, is in real school choice environments where priorities may be coarse, are they qualitatively different effects? And notably, there is empirical work that documents negative relative gains, that is, documents that actually sincere students are better off. So this does not correspond to the theory. So here's an example. We have 2 schools, S1 and S2, each has capacity 1 for simplicity, fully course priorities, which means that if more than 2 students top rank the same school, there's a draw to see who gets admitted. And the students are unaware of the results of this draw when they submit preferences. And there are 3 students, I1, I2, I3. Each of them has utility of 3 for the top school for S1 and utility of 2 for S2. I2 and I3 are sophisticated. Would I1 rather be sophisticated or sincere? So if I1 is also sophisticated, the only symmetric equilibrium, symmetric here is for simplicity, we're going to drop that soon. The only symmetric equilibrium is the all mix. And if you're going to solve for equilibrium, it's very simple. You're going to see that each of them ranks truthfully with probability 0.8 and swaps the schools with probability 0.2. Calculate, you'll see that each of them, in particular I1, gets expected utility of 5/3. Now, what happens if I1 is sincere and everyone knows that? Note that in this symmetric equilibrium, I2 and I3, each of them are indifferent between lying and telling the truth. That's why they're mixing. If I1 is sincere and everyone knows that, then I1 ranks S1 greater than S2 with probability 1. This pushes I2 and I3 to prefer to manipulate more. So the only equilibrium in which I2 and I3 play symmetrically, if I1 is sincere and they know that, they tell the truth with probability 0.6 and they manipulate with probability 0.4. And note that in this equilibrium, there is less competition for I1 for the school that he likes. He crowded out the others, and therefore he gets higher expected utility. They get lower expected utility because they rank S1 higher with a lower probability. So I1 prefers to be sincere as long as everyone knows that and best responds to that. And we can think of I1 as being a Stackelberg leader in some kind of metagame where he first chooses if he wants to be sincere but have everyone know that, or have the possibility of be sophisticated but have everyone know that. And I'm saying Stackelberg leader because that's the right intuition, but we should remember that it's not really the choice of I1 whether to be sincere or not. It's just in our mind. So either he's born sincere or born sophisticated. And question you would now ask is this curiosity prevalent in a large random market? Is it prevalent for any equilibrium and not just solving for specific symmetric equilibria? So here's our model. There are n schools, each with capacity 1, fully course priorities. Again, very, very simple. N students. We fix U1 and U2 to utility levels. U1 is greater than U2. We also require U2 to be greater than 2/3 of U1, having them not too different to avoid certain boundary effects, but this is quite generic as it is. And for each student, we uniformly and independently draw her first and second choice schools. She's going to get utility U1 if she gets her first school, U2 if she gets her second school, 0 for other schools. And each student independently is going to be sincere with probability P and sophisticated with probability P. And everyone knows these realizations. So in equilibrium, sophisticated students best respond. Sincere students obviously tell the truth. The equilibrium is not with respect to them, it's with respect to the sophisticated students. And here's our theorem for relative gains, basically an anything goes kind of theorem. There exists a constant fraction such that for any large enough n, there exists a set of sincere students of expected size at least tau n, such that each of them strictly prefers any equilibrium had she been sophisticated to any real equilibrium, that is, in which she is sincere. And for any equilibrium among the sophisticated students, there exists a set of sophisticated students of expected size at least tau n, such that each of them strictly prefers any equilibrium had she been sincere to the given equilibrium. So we have a constant fraction of sincere students who want to be sophisticated, constant fraction of sophisticated who want to be sincere. Also, by the same argument, a constant fraction of sincere who prefer to stay sincere and sophisticated who prefer to stay sophisticated. So anything goes, basically. And we identify that actually this anything goes kind of thing is actually the superposition of two effects. There's a positive and a negative effect to being sincere. The negative effect, not responding to excess demand, is the effect identified by Patak and Sermes. We talked about it. If there's excess demand to my top school and I have no choice there, I should top rank my second school. We talked about that. And if I'm sincere, I cannot do that. That's a negative effect of sincerity. The positive effect, as we've seen in the example, is crowding out others. If I commit to being sincere, to playing sincere with probability 1, I'm going to crowd out others. They're going to best respond by putting less mass on my top school. And notably, this completely disappears in the special case where all priorities are strict, the special case studied by Patak and Sermes, since in that special case, once everyone submits their preferences, the BM outcome is deterministic. There's no lottery if many people sign up to the same school. And in that case, think about how you would crowd out others. If I is harmed by the competition of J for school S, then I committing to apply to S will not deter J, because the fact that I is harmed by J means that J has higher priority, period. There's no lottery there to determine who gets it. Either J has higher priority at that school or I does. There's no middle ground like there is with course priorities. And in particular, there's a discussion in the paper. I urge you to take a look. And the market structure really determines which of these two effects prevails. And in particular, how the different parts of the markets are coupled and intertwined to each other. It determines the relative strength of each of these effects and determines which one prevails. And in the large random markets, we have small sub-markets where this prevails and small sub-markets where this prevails. And this leads to the anything goes result. So let's talk about absolute gains. Would I, if I'm sophisticated or if I'm sincere, be better off under BM or under DA? Once again, Patak and Sermes study this question in a strict priority environment, and they show that sophisticated students always, at least weakly and many times strictly, prefer the Pareto dominant equilibrium of BM over DA. And we also talked about this with arbitrary priorities. I gave this as motivation earlier on. Abdul Kadiroglu et al. Also prove absolute gains when all players are sophisticated, even with coarse priorities. Their analysis, nonetheless, as notably pointed by P. Troyan, is sensitive to various symmetry assumptions. Once again, we have mixed empirical findings, certain papers showing that BM should be preferred by sophisticated players to DA, other papers showing that actually they should prefer DA to BM. And once again, we have an anything goes kind of result. There exists a constant fraction tau, such that for any large enough n, there exists a set of an expected fraction of at least tau of the sophisticated students and at least tau of the sincere students, such that each of them prefers DA to BM. And there exists an expected fraction of at least tau of the sophisticated students and at least tau of the sincere students, such that each of them prefers BM to DA, the other way around. All these preferences are strict. So once again, anything goes, and once again, we identify two competing effects that cause this. So There's the positive effect of reduced competition. This is the effect identified by Patak and Sermez. My only competition for the school that I rank first are other people who rank that school first, not people who rank that school second. Or if I rank some school second, my only competition are the people who rank it second or first, not those who rank it third or lower. And the negative effect that we identify is that of reduced options. I need to ex ante choose only one over-demanded school to apply for as my first school. If I apply to some over-demanded school as my second school, I'm not going to get in. It's going to be completely filled in the first round already. And once again, this completely disappears in the special case of all strict priorities studied by Patak and Sermez. Once again, since the BM outcome is deterministic, in equilibrium, I'm going to get into the school that I rank first. Otherwise, I won't rank it first in equilibrium. I'm going to rank something else first in equilibrium, and I'm going to get there. Only if the BM outcome is randomized due to tie breaking do I need a plan B, and I'm harmed by the fact that I need to choose only one plan A, and basically I have to give up my plan B due to BM immediately accepting in the first stage. And we have time for an example to drive this point home. So assume that we have two schools, S1 and S2. Once again, each with capacity 1. All priorities are coarse. We have n students. And there are a few students who slightly prefer S1, really by a hair. And many students slightly prefer S2. So under DA, we have roughly a 1/n probability for each match. So basically for school 1, everyone except for maybe one student who gets matched to S2, everyone's going to apply to school 1 at some point. School 1 is going to randomize between them and choose the best one. Same for school 2. So each individual student gets utility roughly 2/n. They have a chance of 1/n at each school. Under BM, that depends. If there are many sophisticated students, then in an equilibrium, about half of the students are going to apply to each school. So each student is going to get utility once again 2/n, about 2/n. But what if there are only a few sophisticated students? In this case, the few sophisticated students and the sincere students who prefer S1 are going to apply to S1. There's going to be lower competition for S1. So all of these guys are going to gain from reduced competition and are not going to be very harmed by reduced options. And the entirety of the rest of the sincere students who prefer S2, most of them are going to have a lot of competition for S2, and they're going to have utility less than 2/n. So they're going to suffer from a negative effect of reduced options. They basically give up their second choice, and they don't really benefit from the positive effect of reduced competition. So we see that these two effects apply equally to sincere and to sophisticated students. And once again, the market structure determines which of these prevails. So to sum up, absolute gains, that's what we talked about just now, BM versus DA. There's the positive effect of reduced competition and negative effect of reduced options. Relative gains, that is, if I'm sincere or sophisticated. So if I'm sincere, there's the positive effect of crowding out others, the Stackelberg-Leader effect. There's a negative effect of not responding to excess demand. And as we've seen, these two effects, the positive effects of being sincere and the negative effect of BM, completely disappear in the special case of all strict priorities, and that's why Patak and Sonmez identify the other two effects only. But this, I hope, is a more complete picture. And as I said a number of times, market structure ultimately determines the relative strength of each of these effects. And I urge you to take a look at our discussion. And the main point is that mechanism designers, in order to choose a mechanism, in order to tailor a mechanism for a certain environment, should really understand the priority and the preference structure of that market, of that environment, in order to understand what the trade-offs are, who wins, who loses, and who has an incentive to do what. Thank you so much. Mm-hmm.
So even if people are sincere in the mechanism, you still wouldn't get stability, of course.
No, Boston mechanism is not geared towards stability, but yeah. That depends on whether you have school priorities or if schools are completely coarse, then you can use TTC. Yeah, if otherwise it's well, TTC would also be unstable. There are a variety. Really, you need to understand the market, the preferences in the market, and your desideratum, of course. Okay. Thank you. Thank you.